first section of chapter 5 is something that we've talked about with many other different functions, but now we're going to talk about it with a quadratic function. And so basically what we're going to do is we're going to start by talking about transformations of functions, and then we're going to look to connect them to a specific way to write an equation of a quadratic, which is called vertex form. Okay, so before we get started, first you need to know what a quadratic function is. And basically, it's a function where x is squared, and the shape is a parabola. Now you've seen... Oh, come on. You've seen a parabola before. There's one right there, right? Some of you have played Angry Birds before. When you shoot your little bird through the air, just like it follows that arc or that U shape, just like this little bird did to hit the pigs. Okay? And parabolas can take any shapes. For example, they can be much flatter, like that, score a bunch of points, much flatter, but still have that preserved U shape. Okay? They can't split like that bird just did, but they do make a nice U shape for parabolas. Okay? And really, we care about parabolas because anytime we talk about throwing a baseball or shooting a cannon or doing pumpkin chunkin' where they launch pumpkins flying through the air, those all follow, any projectile follows that U-shaped parabola graph. So it's really important that we have a good understanding of them. Okay? So, the parabola represents the graph. The function is a quadratic based on the fact that the x value is squared. Okay? Now we can do transformations of a quadratic function. I'm going to give you this chart that really represents all of the transformations that we've talked about so far. Okay? But remember, if it's horizontal, it's done to the input, and if it's vertical, it's done to the whole function. So we're going to start to look at that a little bit specifically with quadratics. Here's a couple examples for you. Using the graph of f of x equal to x squared as a guide, describe the transformation, then graph. Okay? When we look at this, we see x minus, and then in the parentheses, we're subtracting 3. So that automatically tells us we have a horizontal translation to the right 3. Outside the parentheses, we see a minus 2. That tells us we're going down 2 units. So right 3 and down 2. Which is awesome, because if we actually graph this, if green is the original x squared, then we've moved our entire graph right 3 units and down 2 units, and now the vertex is at this little point right here. Okay, so we've not only can we identify the transformation based on what we see in the equation, but we can also look at the graph and go, yeah, we totally got this, right? Okay, so let's do another one. This one's a little bit different, and this is why I get on some of you about where your parentheses are in terms of your exponent when you have a coefficient. Okay? In that first one, we have 2x in the parentheses, so we're thinking with a horizontal, either stretch or compression. Okay? It would be easy to say a stretch of 2, but for horizontal, we have to think in terms of 1 over b. So 2, being multiplied by x, 2 is actually 1 over 1/2. Okay? That's going to be difficult for you to wrap your brain around, but we're going to practice it. Which means that this is actually going to be a horizontal compression by 1/2. Now the one on the right looks really similar. All that's been dropped are the parentheses, but now because there's no parentheses, we're dealing with a vertical stretch by a factor of 2. So here's 3 graphs. This green graph, that's the original x squared. The red one represents a horizontal compression of 1/2. That makes sense. Originally when we were here at negative 1, 1, now we're here at negative 1/2, 1. Okay. Or up here where we're at negative 2, way up here at negative 2, 4, we've moved in 1/2. Okay. The vertical stretch by 2 is different. Now we gotta look in terms of how the y values are changing, because it's vertical, right? When we're here at negative 1, 1, now we're up here at negative 1, 2, because we've multiplied it by 2, a vertical stretch. Okay. What's interesting is when you look at this, the red graph and the blue graph are not the same. Okay, they're not the same by any means, so we really need to be careful when we work with these. Okay, I want you to try too. I'm gonna make it happen. I'm gonna pop it up here. You give it a try. Using the graph of f of x as x squared as a guide, describe the transformation, then graph. X plus 4, the quantity squared, minus 1. Just right now, really quickly, in your notes or on the left-hand page, which would be a great place to make this happen, do a little output. I want you to do a little writing. Tell me what you think's happening here. Make it happen. Okay? that's a +4 on the x, which means we're moving left, right? Because we have to think in terms of opposite. Horizontal, we have to think about the opposite. Whether it's the opposite direction, meaning like minus a negative or minus the positive or whatever, or in terms of the reciprocal, when it's a stretch or compress. Here we're going left 4 units and down 1 unit. And then when we graph it, we can clearly see that our vertex has moved left 4 and down 1. Okay, that's awesome. The graphing it makes this way easy. Okay, I use Desmos to graph all these because I knew it would give me beautiful pictures, but your TI-84 will totally do it too. Okay, here's another one for you to try. A little bit different setup. -1/4 x squared. Okay, you don't see any parentheses, so you're thinking vertical. And in your mind, you might be thinking a vertical compression, because it's less than 1, a vertical compression of by a factor of 1/4. Okay, but this is actually a little bit different. You're right, it's vertical compression, but when we introduce that negative, it's a reflection across the y-axis. Okay? It's a reflection across y. So when we graph it, we can clearly see that the red graph has been now tipped upside down. That looks more like our Angry Birds flight that we looked at, or the flight of a baseball or a football or whatever. But then how do we show vertical compression by 1/4? Well, here, when our graph at -2 was supposed to be 4 tall, if it was just a reflection, we'd be down here at -4. But we're not. We've compressed it down and pulled it in by a factor of 1/4. Okay, so that's vertical compression by 1/4. Whatever y is, we've squished it down now. Now it's only here at -1 instead of being at -4 to match a perfect reflection if we just had -x squared. But we don't. Okay? So this one's a little bit tougher. Watch out for that negative. That negative is going to tell you reflection across the x-axis. Okay? That's my bad. Okay? So that should say across the x-axis. That's my fault. That looks way better. Okay? All of these transformations are connected to what's called vertex form. And vertex form is a specific way to write the equation of a parabola. You maybe haven't seen this before. But vertex form incorporates A, which involves vertical stretch or compress and a reflection across the x-axis, H, and K. And the ordered pair HK will always tell you the vertex of the parabola. We use vertex form to write translated functions. Let's look at how we actually do that. F of x equals x squared, it's our starting function. We want that to be vertically compressed by 1/3, translated 2 units right and 4 units down. There's vertex form. Well, fortunately, from the problem, we know what the values are supposed to be. A is going to be 1/3 because we're vertically compressing by 1/3. H is 2. We're going to translate 2 units right, positive 2 units right. And K is -4 because we're going down. So, the new function g of x should be 1/3 times the quantity x minus 2 squared, and then we're going to subtract 4 on the very end of that. The vertex of this function is at 2, -4. Okay. You try one. These aren't too tough. Oh wait, I'll show you one more. My bad, sorry. Not quite ready for you to try unless you want to try along with me, which would be pretty cool. Here we go. So we're reflecting across x, translating 5 units left and 3 units up. Now, if you remember back, way back to the beginning. No, just kidding. We're going back to here. This A also can tell us if we're reflecting across x because it will be negative. So when we reflect across x here, without the stretch or compress, we're just going to keep it as 1, but make it negative. So that's why A is -1 here. That represents this lovely reflection across the x-axis that we love so much. 5 units left, H equals -5, and 3 units up, K is a +3. That arrow is so long, I love it. Okay, anyway, so g of x equals negative, because that's what A equals, x plus 5, and then we square that, plus 3. Okay, this parabola has a vertex at -5, 3. And what's interesting about this one, because it's reflected, it's going to make more of an upside down U. This actually could represent the flight of a little Angry Bird guy. And then that vertex is when he's at the highest possible place in the air that he can be. We're definitely going to do some talking about that. That would be his maximum height. And we'll do more talking about that when we get into actually looking at finding the vertex, and as well as finding the axis of symmetry. Oh, it'll be so much fun. But for now, love this equation. Substitute in. You try. One last one for you to try. F of x equals x squared. You're going to vertically stretch by a factor of 3 and translate 6 units left. There's vertex form. Give it a try. Figure out if you can, decide if you can figure out what A equals. Figure out what H equals, and figure out what K equals. And then write the equation. You can do this. I know you can. Push pause and make it happen. How'd you do? A is 3. Not a tough one to pick out. H is negative 6. May need to be a little bit careful there. K is actually 0 here. K is going to be 0 because we're not going up or down. We can already tell what the vertex is of our parabola. Negative 6, 0. So G equals 3 times the quantity x plus 6 squared. And then there's no plus on the end. Okay? So that's going to be our function. Now we're not going to try and do squaring anything or distribute the 3 or anything like that. Right here, this is finished form. Don't try and make it look better, because in doing so you're actually going to make it worse. Okay? As we start talking about quadratics and stuff like this, and completing the square and all sorts of fun stuff, and factoring, and oh my gosh, it's going to be awesome. Then we'll talk about why and how and the best way to work with this, but in the meantime, just leave it like this. Leave A out in front. It's supposed to be out in front. And then leave H and K where they are as well. Obviously here there's no K. Okay? So, hopefully you know how to understand if it's been translated, and explain the translation, and then also then take a translation and go to vertex form. So we're doing a couple different things. We're starting with an equation that looks like it's in vertex form, and writing what transformations have happened. And then we're starting with plain old vertex form and plugging in some transformations to make a new equation. Okay? You're going to do just fine at this. I know you will. It's going to be great, people.